Right. Yes, so Reinhard already set the stage with this very beautiful experiment that we had been conducting over all these decades. Indeed, I'll try to continue with this, and I want to basically also rewind a few hundred years backwards. Reinhard showed this experiment that was possible with new technology, but of course, people have been thinking about gravity for a long time. And whether Galileo really made this drop power experiments, as we would call it today, whether Newton really saw the apple falling in front of his eyes. Certainly with Cavendish and others, real experiments were conducted, and astronomy already played an important role from the very beginning. You see a map here on the top right, which is in the Library of Congress, where people already, astronomers who noticed the deviation of the Mercury orbit and postulated that this may be caused by an additional planet, which they called Vulcan, would have been located between Mercury and the Sun. But of course, that deviation from Mercury's orbit from an ellipse was explained then later indeed by Albert Einstein's theory of gravity, which really revolutionized our thinking and really threw away hundreds of years of thinking of how gravity works and really replacing it by the curvature of something we call space-time. And this was beautifully demonstrated then in this experiment you've seen at the bottom left, the bottom right, which is the solar eclipse exhibition to 1919, where light, as we have seen from later from Reinhard and my talk, is bended by the gravity in the space-time around the sun. And that's also a beautiful example because this exhibition was initiated by Arthur Eddington in Great Britain, who was, of course, he proposed that experiment during the war to test a theory that was proposed by a German. So that's a very nice example of how societies can work across these dividing lines. There are many experiments that we have done by many people to test gravity. This is one way of trying to capsulate this. I plot here the space-time curvature of a system on the y-axis and the gravitational potential of the orbit that is being experienced on the x-axis. And you see a number of experiments. You already seen this beautiful work from Reinhard here. I'll talk mostly about pulsars, as we alluded to, and gravitational wave detectors I've also mentioned by Reinhard are in the top right of the diagram. So I'll come back to this diagram at the end. So I will point out that everything that is here marked in yellow is actually reusing radio astronomy techniques, and that's why I'm an astronomer, radio astronomer, and I'll talk about these experiments in this solid time. Radio astronomy is indeed an ideal tool to test gravity because we observe photons which are of low energy, but they're actually mostly resulting from very high energetic processes and compact objects. We can receive lots and lots of photons, and we can easily multiply them, combine them, and let them interfere, and that lets us to build huge telescopes on the size of the Earth and beyond. And you see an example, for instance, here at the bottom right, which is the new beautiful Meerkat telescope in South Africa. On the left, you see our own telescope near Bonn. Gravitational, so radio waves basically propagate the whole universe, including that dust that Reinhard showed, looking right into the galactic center to the edge of the universe, and we see the cosmic microwave background as a remnant of the Big Bang that created the universe. We can also get polarization information, so we can get information about magnetic fields, and because we get so many photons, we can resolve the universe on nanosecond timescale. So I'm mostly interested in objects called pulsars. These are rotating Newton stars, the most extreme objects in the universe that we can observe. And the density inside is about 10 times the nuclear density. And they emit a radio beam along the magnetic axis. This is inclined to the rotational axis. And whenever that beam points towards you, you see a tick, and that tick is tied to the rotation of that Newton star. And that is indeed as stable as the best atomic clocks that we have on Earth. And so if you think about general relativity, you think about space-time, you have here the beautiful example of very compact objects having a clock attached to them, and that's what we use for our experiments. The experiment is very simple. As astronomers, we can only watch the sky. We can try to see how these objects, like Reinhard's S-stars, move around a black hole. We observe how our clocks move around a companion, and we trace that to precision about 30 meters in their orbits. It doesn't matter how many light years, thousands of light years these things are away. And by that, we can compare what the theory predicts compared to what the movement is actually on the sky. And so we have done it, for instance, with one beautiful example. This is a pulsar we discovered nearly 20 years ago. Actually, it's a pair of two pulsars orbiting each other in just 147 minutes. They are highly relativistic orbits. They have orbital velocities of about 1 million kilometers an hour. And if you actually see the system from nearly edge on, as you can see it now, you can actually see eclipses of one pulsar by the other. And it's a beautiful laboratory to test lots and lots and lots of different relativistic effects, which are listed on the right-hand side. And I'll show you only some of them. Maybe the most important one is the emission of gravitational waves, because pulsars indeed were the first evidence that gravitational waves exist. This was awarded with Nobel Prize to Hulse and Taylor in 1993. We see the same effect here as the pulsars orbit each other. The orbit loses energy due to the emission of gravitational waves. The orbit shrinks by about 7 millimeters a day, or 107,000 picoseconds a day, which we can measure. And the effect is that is shown on the right-hand side. Is the shift in the closest approach, the function of year, and the orbit shrinks and shrinks, and so the pulsars reach the periaston passage earlier and earlier. And the red line is the prediction of general relativity, and the blue points are my data points. And that is the confirmation of the properties of gravitational wave, which is about 1,000 times more precise than what gravitational wave detectors can do. In fact, it's so precise that we now have to take into account that the pulsars emit electromagnetic radiation and thereby lose energy, because E is equal to mc squared. And if we wouldn't take this into account, even though this is only 10 to the minus 21 of the mass of the Newton star per second, our data wouldn't quite fit. We also see light propagation in strong gravitational fields. The light is bent just like around the sun. It's also bent around Newton stars. Again, we can see this nicely in our data. When the two pulsars are aligned along the line of sight to the Earth, it takes a bit longer for the photons to go through this dip in space-time, and takes an additional 120 microseconds for us to reach here on Earth. And you can see the data on the right-hand side. And again, the red curve is the prediction by general relativity, and the blue are our data points. In fact, the data are now so precise, we have to take into account that the speed of light is finite. So when the photon leaves one pulsar, it travels about 3 light seconds to come across to the other pulsar, during which the other pulsar, B pulsar, has slightly moved. And again, if you wouldn't take that into account, our data wouldn't fit. We can even look further. So what I showed you, the experiment that Eddington was initiating in 1919, we see the same thing here. In the pulsars, the light is bent in a curved spacetime around the companion, and so the photons have to be emitted at a slightly different angle in order to compensate the bending to reach us on Earth here at the bottom. And after superior conjunction, it has to be emitted in a slightly different angle earlier to compensate in the opposite direction. And this is here the signature in our data. And this allows us even to determine what the direction of the spin of the pulsar is, in which way it rotates on the sky. So there's a number of facts which I could go on and explain, but in shortness of time, and let me just summarize here the test of general relativity. In fact, we can do this test for alternative theories of gravity as well. So what the table shows here is basically the kind of effect which we see on the in our data, and the right column is the comparison of our observations with the prediction of general relativity. And as you can see, relativity has passed all these test flying colors. We are currently searching for many more extreme objects, producing lots and lots of data, which is another interesting talk by its own, how we deal with this data challenge that society will also face in a few years. So the astronomy is really a trailblazer here also for technology development that society can benefit from later. I also mentioned one thing that I explained in a paper that's lying on the table was spin precession, which is one of my favorite tests of the general relativity in the systems. Reinhard already showed the pictures of the black holes that we have obtained in the last couple of years. On the left-hand side, you see the image of M87, which is in the core of a galaxy much further away than the center of the Milky Way, which you see here on the right-hand side. And these are the images. It's also caused by the light bending effects. The idea is, of course, is not new. Basically, when the photon approaches the black hole, there's a certain distance beyond the photon will absorbed by the black hole, and beyond where this photon can just escape. This is the photon ring that Reinhard was already mentioning. And in this animation that you'll hope to see on the right-hand side, If the black hole is embedded into a sea of photons that swirl around this black hole, as you will see in a minute, then some of these photons will not make it to the distant observer. And so you see a lack of photons in a certain direction towards the black hole. And that's exactly the kind of shadow that we see because the photons are missing in that part of our image. You see this now from the front in a minute, in a second. And then you can understand how that image is actually produced. So the image that we produce, again, uses a feature of radio astronomy that we can connect these telescopes across even continental baselines and even to satellites if there's a satellite in space. And we basically bring the data together in one place and combine them, and it's the Earth rotation that basically fills in the gaps we have in our telescope. By having more telescopes and less gaps, we can produce that beautiful image that you've seen. In comparison, the black hole of M87 is 1,000 times bigger than the black hole in the center of our own galaxy. And our own galaxy is just encompassing the Mercury's orbit, whereas in M87, it extends far beyond Pluto's orbit. But how can we test relativity? Reinhard already alluded to that the mass is determining the size of the black hole. It's the only one of parameters to determine the black hole shape. And so by measuring the size of the black hole on the sky and knowing the distance and the mass from Reinhard's observation, we can actually compare what we see on the sky with the actual size that we measure, and the agreement is good within 10%. It's much less accurate than what we can do with radio pulsars, but it's a complementary nice test. So the question is again, is Einstein right? Or the Australians, I think, actually got the question better because they asked, was he wrong? Because we can never really prove a theory, we can only falsify it. And so this is really the name of the game. And if you work on testing general relativity, you get basically a letter, a phone call, or email every week, every month, where people tell you that general relativity actually doesn't work, and you massage the data, or even worse. And there's some even worse examples. I won't give you the URL because that website shouldn't be graced with any visit. But basically, it's really, they're almost racist comments about Einstein being a Jew with this theory. So it's it's important that we say what we do. It's important that we show what our data tells us, and we should be able to accept the facts, even if people don't like the result. I compare it with people who still believe that the Earth is flat. More practical issue that I want to raise your awareness of is that we are actually in the process of losing the access to our sky. There are so many satellites, and the proposal is there will be tens of thousands of satellites for mega constellations to bring the internet at places in the Earth when you really don't need it. And this mass of satellites does not only cause a lot of space debris if things collide and become smaller pieces which collide in smaller pieces, collide in smaller pieces. And you can see this kind of diagram here of how the number of objects in the Earth orbit has increased dramatically over the years. And there's an avalanche effect called the Kessler effect, which makes it really difficult, not only for human space flight, but also for observing, for instance, with our satellites. This is the damage of the Hubble Space Telescope endured from space debris. But it's not only that, it's also that these satellites, they're going to reflect light, they already do, and this night sky will not be the way we used to be anymore. There's no space on the Earth anymore where we can look at the sky without being disturbed from satellite traffic. And if that continues, our children, our grandchildren, our generation of future astronomers won't be able to watch the night sky anymore. This is not only in the optical. Here you see some nasty examples of the Starlink satellites, for instance, but also OneWeb. But also in the radio, the pressure, the commercial pressure of telecommunication companies to get more spectral videos of cats or whatever, is really narrowing down our ability to watch the sky. So I conclude, Einstein has said he once mentioned that there are only two things that are infinite, the universe and human stupidity, and he wasn't sure about the former. That's not confirmed. I rather sort of want to finish on the positive side. This is a citation that is actually confirmed. he said in a letter to Arnold Sommerfeld, there comes the pedantic precision of astronomy to the rescue, which I've ridiculed silently so often in the past. So thank you very much.
Thanks very much, Michael, for this beautiful talk, covering a lot of ground, both in terms of testing general relativity and these fantastic images of the shadow of the black hole, but then also warning us about some of the threats that we have. Again, opportunity for one or two quick questions. Yes, go ahead, please.
Is in terms of the entire gravity and gravitational waves. How the results of radio astronomy compare to LIGO and the other things? How should I look at this data together?
Can you? Thanks. They're truly complementary. Basically, what we do, both strong field tests of gravity, but they use the highly dynamic. They can use high dynamic space-time waves in action. We can do the more precise tests, more static. So it's a beautiful combination of the two, and it's eventually the combination of the two results will bring us the best test. So.
Are all the numbers consistent now? So the quantity that comes, the quantitatively, how are the comparison of the two things? I think qualitatively I agree, but quantitatively, how good are we getting there? So the question, you had a great final slide, so let's see how these two views come together on that.
They're beautifully consistent. It's an amazing theory. And that's a beautiful theory. It's one of the theories which has so much predictive power. It uses experiments and methods and objects that were not even known when Einstein wrote down this theory. For me, this is the most amazing thing about it at all.
Martin, would you like to comment on this? Do you have any comment or question on this part? I'm not sure whether we lost. Oh, sorry. Yes, please go ahead.
Yes. Well, I'd just like to say how amazingly productive pulsars have been, because they were discovered, as we know, almost accidentally in 1968, and they have been superb laboratories for testing dense matter, and it's quite amazing the precision that we get in the results that Professor Kramer has just presented. And we can expect far more in the future. So wonderful experiments.
Yes, briefly from a layman's point of view, the shrinking of orbit as a result of a gravitational wave, does that lead ultimately to a shrinking of all elements in the solar system? And would that lead then to draw the elements being drawn closer and closer to the sun?
First of all, indeed, in 85 million years, these neutron stars will collide and they will form a black hole. And by the way, this will produce all the elements beyond iron. So this is one way of making the gold and platinum, all these wonderful things. Yes, eventually gravity, you could say, everything would attract to its point, but everything has also momentum. So it would take a long time for this actually to happen. So on a local scale, yes, it will merge, but on a global scale, on a more distant scale, we don't have to worry about it. I mean, even if the sun would be, for instance, would be replaced by a black hole, you wouldn't notice. It would be cold, but from the gravitational point of view, you wouldn't see a difference.